Okay, we're gonna have a video today on on a hypothesis test for the difference of two proportions. So this would be if we would like to, if we were trying to find evidence that two populations have a different proportion of a certain characteristic. Maybe that's preference toward a law. Maybe that's um, a different proportion of aged people. So maybe there's a higher percentage of adults in one city versus another city. And those are some just simple examples, or just proportions of successes in maybe some psychological testing that has been done on groups of people. So we're trying to figure out, is it possible that there is or is not a difference in the actual proportions of successes in two populations. So here's an example. This is the first of two videos on these problems. And try to get this first part in here just so we understand the situation. Then we'll actually run the hypothesis test. So this first video is actually about simulating this because I do think that this is something that's very important, and this is how people understand more complicated processes. So here's your question. A survey organization conducted telephone interviews in December 2008 in which 1,009 randomly selected adults in the United States responded to the following question. At the present time, do you think television commercials are an effective way to promote a new product? Of the 1,009 adults surveyed, 676 responded yes. In December 2007, so a year before, on a similar survey, 622 of 1,020 randomly selected adults responded yes to the same question. So the question is, do these data, so this is your data you have from two random samples, suggest that the proportion of adults in the United States who would respond yes to the question has increased within the year? So I would like to just set this up because this is a question about a hypothesis, and we actually learned we could go and do a confidence interval for this. We learned how to do a confidence interval for the difference of two proportions. So but we're going to do a hypothesis test. So the first part of any hypothesis test, and this will not the beginning part of this video, but as we go through the video, this will give you a good idea of how to set up a free response question for that shows full understanding of the problem. Okay, so first thing, you got to check conditions to see if you even can proceed with some inference. So inference, again, means we're trying to learn something about a population, or in this case, about two populations and their difference. So first part, let's check. Let's write some hypotheses and check some conditions. So the first part, let's write some hypotheses in here. let's use purple today. Okay, so your hypotheses for this, the null hypothesis. Okay, so what do you expect to happen, or what's the initial expectation? The initial expectation is that, until you take the second survey in 2008, you're going to assume that this proportion from 2007 that responded yes is probably the same. So our initial expectation before we do this second survey in 2008 is that the proportion is the same. So, or in other words, the difference is 0. So I'm going to write that in two ways. P with a subscript of, let's say, 2008 minus P with a subscript of 2007. That difference we expect to be 0. Another way you could write that is P subscript 2008 equals P 2007. Okay, so what's your alternative hypothesis? So what are we actually trying to determine here? So the alternative hypothesis is that, what are they asking about? Okay, they're trying to see who responded yes to the question increased within the year. So we want to know has this difference increased? In other words, is the difference no longer 0 but bigger? So which means that, another way of writing that, which is totally fine, is the proportion bigger in 2008 than it was in 2007. So either one of those sets of hypotheses are okay. So you can either write it as the difference or subtraction, or as their equivalent. I think for understanding the question, this is a better understanding. But for the statistics, writing it this way is actually going to make a little bit more sense. So it doesn't matter which way you write it. Okay, so so let's check some conditions for a second. So to do inference, we have to make sure we have everything set up. So this is all part of showing a complete understanding. So you have conditions that need to be checked. And I'm actually going to draw a little table for this. I think it is helpful to organize some of your conditions, especially with two populations. So these will be your conditions to check, and then we'll do these conditions for 2008 and 2007. So in 2008, first of all, did it say they had a random sample? Yes, it says right there, randomly selected adults. So there was a random sample taken in 2008. Okay, did we have the same thing in 2007? Yes. So we had a random sample taken in 2007. And these are independent random samples because, and we'll talk about that here in a second, like with the last one. Okay, normal checks. All right, so to do a normal check, we have to do n times n in 2008 times, okay, so we don't know the actual proportion in 2008, but we do know the sample proportion in 2008. We have that data right up here where it says 676 of the 1,009 adults responded. So we do know p hat. So we can use p hat to do our normal check. So p hat in 2008, we want to check to make sure that that is at least 10. And we got to do the same thing with n times 1 minus p hat. Okay, we got to do the same thing. I'm going to save us a minute here just for a second. You should work those out, and you have to show your work to check those. I'm going to let you check those, but I'm going to put down what p hat for 2008 is because I think that's an important part of our analysis here. Obviously, that's our statistic. It's 676 out of 1,009. And then we need the same thing over here in 2007. So all of these would be 2007. Again, you have to check these. You do have to show your work. It shows you're completely checking the conditions. So I will let you check those. That's part of your response. And then in 2007, p hat was what was it? 622 out of 1,020. So 622 out of 1,020. Okay. All right, and then finally we have our independence check. So the sample size in 2008 was 1,009. Okay, that is, we're talking about U.S. adults randomly selected. That is certainly less than 10% of all U.S. adults. And then the same thing holds true in 2007. So why is this important? First of all, that means all of the individual responses in 2007 were independent of each other or likely to be independent of each other, and the same thing in 2008. And moreover, like, it's unlikely that anybody who was in the random sample in 2008 was also in the random sample in 2007, since this is a huge population. So these random samples here are independent of each other. So these should be our conditions. They are all verified. You could easily see that the number of people, if you do 1,009 times p, you're going to get 676 here, and then you get the remaining over here. They're definitely larger than 10 for each of those. So all of these check out. So we can proceed with running our hypothesis test. Okay. So this part right here is all part of a good setup for a hypothesis test for the difference of two proportions. I'm going to add one piece up here that I did not add at the beginning, just so we can understand what was going on. You must define what P sub 2008 and 2007 actually represent. So these are your parameters you must define. your parameters, P 2008. So what are we talking about here? This is without the hat. This is referring to the population. This is population parameter. This is your sample statistics. So P in 2008. What are we asking about? We're asking about the true proportion of adults in 2008 that responded yes to the question. And then P 2007 is the same sort of definition, except we have a different year. So we have to define what those are to make sure our notation and we're clearly communicating what we were talking about. So the context must be there. You have to say how they responded, because if you were talking about no's, then this would be a different story. So this is fine for a definition, and it's the true proportion we're interested in. So so we're going to run a hypothesis test, and I'm going to actually carry out the formal hypothesis test in the second video. But I want to do for the last couple minutes here on this video is simulate this. Like what should we expect to happen, and how do we see all of this, and how do we make a conclusion informally? I do think simulations are important, and I do think it's going to be something that you might encounter on the AP test this year. So I want to make sure we address that and we keep doing some simulation-based stuff. So, okay. So what do we know? We have two random samples. We have this sample data. Okay, so what's our expectation going into this? Our expectation is that the true proportion in 2008 of the respondents for yes is exactly equal to the 2007 proportion. So what do we expect to happen then when you take random samples? Well, if you're expecting them to be equal, then when you come down here, these p hats, these sample proportions, should be pretty equal. Or in other words, the difference between them should be pretty close to zero. So I have a simulation set up that shows us that that is what we should expect to happen. So if I come over here, I have this code. Some of you are interested in programming. You can ask me on your own time. Would love to talk to you about it, about statistical stuff. But this is going to run 1,000 simulations. In other words, this is going to take 1,000 random samples from each population. The size of population 1 is going to, or sample 1, I'm sorry, is 1,009 for 2008. And then we're going to have 1,020 for 2007. P, I'm picking a proportion right now just for simulation purposes, but P is what we expect both of the populations to be. So in other words, when I say P1 is equal to P and P2 is equal to P, in other words, I'm telling you that we expect these two proportions to be exactly the same. So what this is going to do is going to take random samples, and it's going to calculate the following statistic. The statistic it's going to calculate is P hat in 2008, which in my simulation is 1, minus P hat in 2007. And it's going to calculate that 1,000 times. And if we're lucky in our simulation should be centered around 0, because that is our expectation. We're building this around the expectation that there is no difference in proportions. So that's what this is going to do for us. So I'm going to do it 1,000 times here real quick. Takes a second to run through here. Okay, so here's our histogram of P hat 1 minus P hat 2. So this is P hat in 2008 minus P hat in 2007. Look at that. The expected value, the center of this thing, is right at 0. So in other words, if we're truly believing that there is no difference, then it makes sense that our distribution of our sampling distribution of the difference in these sample proportions should be centered at 0. I mean, if both populations truly have the same proportion of yes responders, then it makes sense that the difference in the sample proportion should be pretty close to 0. So the question is, if this is what we expect to occur, and notice how normal that looks. then we compare, this is our expectation compared to what actually happened. So let's go to our statistics. What actually happened here? So p hat in 2008 minus p hat in 2007. So this is 6769 minus 6222. What is the difference that we actually observed? And according to my quick calculation here, that difference is 0.06, so about a 6% difference. Okay, so this is what we actually observed. So what do we do with this? This is our observation, actually observed. We go and we look at where does that fall in what we expect. And remember, our expectation is that the difference is 0. So we got to look at this and look about how far away is too far. So we come over here and we look, where's 0.06? Well, here's 0.05, so 0.06 is somewhere out here. And look at that. If I were to put 0.06 on my histogram, 0.06 would fall about here. And we're looking at, what is our hypothesis? A greater than probability, or a greater than statement. So we're looking at the probability, a p-value, of to the right here, so this area. So if we calculate that p-value, to me, this looks like there's only maybe 1 or 2 occurrences that fall at 0.06 or bigger. So our p-value would be like 2 out of 1,000. I did this 1,000 times. So there's only 2 occurrences more extreme than 0.06. So in other words, our sample data that we have, this difference in sample proportions, 0.06, is pretty large. It's much different than we would expect. It's rare. So that means that it is likely, or that we reject this idea that the proportions are equal in favor of that they actually have increased. I mean, we're seeing a larger difference or a significantly larger difference in 2008 versus 2007 at about a 6% increase. And we know that that's significant because 6%, 0.06 falls around here, and that is far from what is expected. And it occurs with a low probability, a low p-value. So when we do this hypothesis test and formally carry it out, we should make the same conclusion, but that is how you calculate a p-value from a simulation. It would be about 2 out of 1,000, so 0.002, and we calculate that from looking at the amount of data in the simulation that occurs at 0.06 or beyond, and that is roughly 2 occurrences out of 1,000. So video number 2 is coming.